hope I give you something useful here. My name is Aris. I work at Credit Karma with a bunch of very talented folks. And today I'd like to talk about functional programming for data science and a little bit about why for loops are bad. The title, kind of the motivation of this talk and the subtitle's motivation come from personal experience. Having come to this conference, many other conferences, having read books, having read a lot of internet, there's a lot of people talking about wonderful constructs in functional programming, the evolution of functional programming, a lot of stuff in machine learning, modeling, data analytics, and so forth. It's just been kind of uncommon to hear about the synthesis of the two, and the two fit together beautifully. I mean, it's just a type of computation. So one is a philosophy and one is a domain, right? And the background behind for loops considered harmful is coming from my own personal experience of, at this point, a number of years ago, I had basically given up on enjoying software engineering broadly. There's a lot of cool stuff in computer science, but the real day-to-day of working in teams, writing code, dealing with stuff was misery-inducing. It made me sad, and I spent less time, I mean, on average, it felt like I was spending way too much time dealing with non-computer science problems, let's put it that way. And after a while, quite on accident, I had learned that it was basically broadly due to imperative and procedural programming. And I'll just call it. So, I'd like to speak about it. So I'd like to start off by just getting a feel on the audience here. How many of you guys are at least aware of, understand functional programming? Cool. How many of you guys have, keep your hands up actually for a moment. Can you also raise the other hand if you've done any type of data science work, modeling, data analytics? Cool. And how many of you have ever committed a bug to production? 3. OK. So this may be of some use to you. Remember, this is fun. So this is why I want to talk about this stuff here. I want to get us all on the same page, at least, about characteristics of what I'm talking about with respect to statically typed functional programming here. So first off, it kind of all comes down to, immutable data. Without immutable data, you're not going very far. If we look at also next of static and strong types, yes, I'm interested in that. I know the closurists out there do a lot of cool stuff, but we'll keep that to the side for a moment. And so static and strong, meaning 1 + 1 equals 2. It doesn't equal 11 sometimes. No magic, weird, uncontrolled conversions. Further, we're looking at referential transparency, which is a fancy way of saying that whenever you call a function, you can actually replace that function with the return value of that function, and it doesn't do anything else with the rest of your program. You can still understand what happened here. You can think locally and not affect the world globally, right? And another concept here is like the separation of the what from the how. An easy way to think about that is imagine a SQL query, guys. Select star from customers where age is greater than 40. Well, I've described a table, but I haven't told you, like down at the assembly level, like what registers and what machine operations I'm going to do in order to compute that, right? So that's a really, really cool property here. And that kind of leads into here, true function composition. So you guys remember in school, you had an f of x, you had a g of x. You could actually do an f of g of x. And you actually get that property here with true functional programming, as opposed to, like square, hole, round, peg. Like if you jam it in there, which computers let you do, you can accomplish this. But I like true function composition here. So I would like to ask you some questions about your code, my code too. So does your code cause interstellar explosions? This has actually happened. If we look at the Mars rover back in 1999, it actually exploded because of confusion between like centimeters and inches, basically metric and imperial units. From statically typed functional programming, like we have types. We model these units as types. I mean, basically that would be a compiler error, not a runtime error on Mars. If we move further, hey, worked for me, didn't work for you, right? This is kind of the ultimate problem. What I'm basically asking is, do your systems, are your systems produced out of small, easy to test, and easy to understand components that work predictably? It's a big question there. A lot of those problems can be solved through some of these FP techniques, such as, again, referential transparency, some of the great patterns that we know about, like monads, functors, applicatives, and not allowing things like global mutating variables kind of all over the place. Well, does your code cause headaches? Is it hard for other people to understand your code? There are ways of improving this as well. Through, like, stop the imperative control flow of using, like, for loops and while loops. Use maps and folds, for example. Use total functions that always return a value. Like, if you divide two numbers, don't throw an exception, return an option. You'll see that in a second. And again, use value immutability, recursion in your design. And again, remember, a lot of this comes down to write big algorithms from small algorithms. Now, if your code is something that you can't easily improve, changing is what we do to code all the time, you're going to be in trouble, right? And one of the reasons why we're scared of changing our code is we don't have any, like, guarantees or static properties of our code commonly. So an important aspect, an important property, really, of functional programming is you get equational reasoning, which is another fancy way of saying, like, okay, if I have this gigantic system, you know, can I split it in half? Can I move these two parts there? Can I replace this component with this component? Those are great properties to have when you're improving and changing your code. I mean, again, that's part of an aspect of true composition. How about you just never throw exceptions? That would help. And again, control your side effects. And another, like, useful component here is, like, using type classes. Again, sometimes you just want to add behavior to types rather than change all the subclassing hierarchy and end up looking like Spark. And the last thing I would say is, is code ceremony. Now, ceremony is great for humans. We like it. We thrive on it. But code ceremony and boilerplate, no. It ends up becoming like cognitive noise. You'd end up seeing like 50 lines of Java lines of stuff, and it turns out only 3 lines do something, and the rest of it is like the Spring framework, right? A lot of, like, functional techniques, such as higher order functions, really help with this. Again, having reliable patterns, such as, monads, bind, flat map, help you out. And again, higher kind of types are huge in terms of removing repeated code. I mean, can't really write a generic monad without higher kind of types. So, where am I going with this? Yes, statically typed functional programming. The bottom line here is, whether you're a business guy or research scientist, is that we want better code. We want it developed correctly faster, not just developed faster. And we want it cheaper in terms of agony and in terms of time cost, right? And there are a lot of, like, great properties from going this route, and I'll talk about them. Parallelism, correctness, expressiveness, compositionality. Now again, looking at the mind of, like, an actual industry data scientist, there's something that matters here. From having worked with the guys and girls on the team at Credit Karma, here's what I've learned. Look, they want better models, they want better data, more experiments. They have a domain that they care about. It turns out that the computers are incidentally there. I mean, very frequently, you have people with PhDs who've been in school, and they're basically saying, like, I have this idea on paper. How do I go from paper into the computer and make it happen, right? These are just incidental tools. They are typically not, again, religiose on the computer science. And this actually matters, because I work with physicists and hard scientists, PhDs, who are, it's not for lack of brains, it's just that their interests are in different places. And frequently, they are just given some tools. They're like, here you go, have you some R, have you some Python. And it works well enough, and that's fine. And again, to at least address the Python problem, look, if you threw a statistician into a company and said, hey, write some Java, write some C++, as was the case in the past, it's not pleasant, it's not great. Versus, you fire up Jupyter Notebook, you import sklearn, you import TensorFlow, you deployed a model, you thought about your domain, you have a job that pays you 6 figures. This is a form of progress, right? So I can't argue with why the reality is as it is. However, let's say Python, for example, is open to a ton of problems that are just common to statically typed, mostly procedural languages. And despite the fact that you might be able to tell that I like functional programming, I want to disabuse you of the idea that it is for free. Now, this is kind of a magic pseudo-fake graph talking about as time and complexity increases and your team, by the way, team productivity. I'm giving you kind of like my experience here. The bottom line here is, look, if in a mythical world all you were doing was you had a 50-line program and that was your company, write it in Python, I don't care, write it in Bash. Do what you want to do, I mean, that would be fine. But in the real world, as your project grows in complexity, as the team grows in size, and especially as people come and as they go, and as time goes forward, needs change, I have noticed that you can actually become more productive, like reliably more productive, if you are clinging to these useful functional constructs, rather than choking on complexity and just burning yourself. Also, yes, I get it. There are many more libraries for Python than for Haskell. I know. So that's the other just reality check to have here, is that if you're just looking for something to work, boom, out of the box, et cetera, why is reality as it is? Well, this is part of the reality. Again, these are unscientific, but I'll just leave them as something you'll believe me. However, guys, functional programming truly is worth it. There are a lot of benefits here in terms of big data computing, parallelism, Hadoop, Spark, all that stuff. It came from map and reduce. Correctness, you're more likely to get it right. Expressiveness also means like you end up writing less code. Less code equals probably less bugs. And compositionality, like I mentioned, true f of g of x. And just to remember, guys, like SQL and Excel, they're actually functional programming languages. So these are not foreign concepts. So, talk about the benefit of parallelism. Look, ultimately, I'm going to give you some, like, here's just like some fakey code that's kind of sparky, kind of data flow, SIO, et cetera. But the bottom line is, imagine like if your use case was this. Imagine you have a bunch of users, their data, and you have some models, and you want to batch score a bunch of predictions, right? For like what products you're going to give to these, to recommend to these users, right? Common use case in the Silicon Valley. Instead of using a for loop, I'm literally using a map. The interesting property of this code is that it's scale invariant programming. I mean, meaning concretely that like if I have a megabyte of data or if I have like a petabyte of data on a cluster, it's the same code basically. And I can swap from, again, one framework to another, and it basically seems like the same thing. Like how many threads, how many computers are operating on here as a data scientist? I don't care. The more you can say, I don't care, it just works, the happier you will be. Let's look at correctness. Now, here's a counterexample of some code. This is a version of code that I have seen like a junior data scientist actually write. Now, the number of ways that this is wrong is just large. You've got type confusion, you have side effects, mutation, and like the really fun thing is if you just run this function multiple times, you get different results half the time, right? And the point is that one of the powers of Python and why people like it is like you can do anything. And I'm saying, well, that's also part of the problem. And if the language kind of encourages stuff, well, you'll get what you incentivize. Although this can obviously be improved in a lot of ways, even within Python. Something else that you can get out of here is, for example, I used to hate compilers long ago with Java, but I really like compiler errors now because I want to have compiler errors early and often. Meaning, like, for example, imagine you're multiplying two matrices here with a pseudo Scala. Yes, you can multiply left times right, and you will get a 5x3 matrix, and even the compiler itself can actually give it to you. But you know how we make mistakes sometimes? The nice thing is, if you do it the wrong way, and you multiply the matrices in the wrong direction, it's a compiler error. This eliminates an entire category of possible mistakes, right? And there are huge numbers of errors that can be just solved just by modeling your projects this way. Another part here is for correctness is kind of like partial total functions, aka unconstrained versus constrained code. So in this, it says Pythonic Python there. Look, besides the fact that I can read English, I don't know anything about this function. It says read file. It might launch the missiles. We don't know what it does. Versus if we look at this, if it's written in pure functional Scala, not just any Scala, look, all I know is read file is a function. It takes a path, file path. It is actually some type of ADT, and it returns the description of a program that when that program is run, it will return some type of useful error type or some type of file. Now, if we look at also expressiveness, have you guys ever taken the average of a list of numbers? And OK, also sometimes your list might be empty. This is a total function. It will work. And you can see it, right? I mean, hopefully it's easy to follow what's going on here. If you do this in a procedural way, well, it does mostly the same thing. It's accomplishing the same thing. I understand that. You know, it uses exceptions instead. But can anyone actually see the bug here? Does anyone see it? OK, there is no bug. I just said that to kind of abuse you guys. I mean, it's literally just the case that we constantly have we constantly have off by 1 errors. We have divide by 0 errors. We have timer errors sometimes. And it's just the point that we can actually get away from this whole class of problems by having a more expressive function up there. I would prefer the first function over the second function any day. Also, if we look at algebraic properties here, I mean, this is a fancy way of saying something you guys already know and love. For example, the algebra of arithmetic. So you guys remember that you learned this in school, like the algebra, let's say here, for any real number, if you go real number plus 0, you get the real number back. Cool. For any real number, if you go times 1, you get that real number back. Like, these are lovely properties that are mathematically universally true. This is good stuff, monoids, right? Here, you can actually easily introduce concepts like this into your code. In this contrived example of just talking about, hey, we've got data, we have learners, we can build models, and then we have properties, it's very much like the same way that you can trust realities about real numbers, you can also have trust in your system, and you can build that in. And here, if we talk about true compositionality, one of the aspects here I like about good FP is that you can separate, again, the what we are doing from the how we are doing it. If you have yourself like a nice embedded DSL, in this case I'm doing like free monady type stuff, but this is kind of the ultimate in terms of having a nice DSL that describes your problem domain, and it's totally compositional and it's totally substitutable. A lot of these things go hand in hand, having true substitution. The cool thing about this, for example, is it's so substitutable and that you could write this one function that does this machine learning pipeline, but you can even substitute what platform it's running on. So scikit-learn, TensorFlow, SparkLink, that's pretty cool. Those are just different interpreters from the free monad world. And cross-language, et cetera. You get to do what you want. And from the perspective of a data scientist, he just, dude just thought about what dude wanted to do, and it just happened, right? And engineering people like, we just make it happen in whatever environment needs to happen. That's just an implementation detail, right? And again, these are just bigger programs from smaller, easily understood programs. And I'd like to finish off on just sometimes the correspondence here is a little almost amazing. It's very beautiful here. So for example, if you guys heard about like recurrent neural networks, some people in the room probably use them frequently. What you see here is like they're used, for example, let's say in translation. Okay, let's say we want to translate from French to German. Now, what the actual neural network is doing here in pictures, for example, if you're collapsing down the French sentence, that's called a fold. And then when you go from that representation into the target language, that's called an unfold. And hey, what do you know? It's basically called, fold by after unfold. This is called a refold. And for example, if people who are steeped in the functional programming world understand things like catamorphism, anamorphism, helomorphism, because Greek words are cool, it's what we have here, right? And if you're just used to thinking this way, it turns out you're used to thinking in some types of neural networks. So that's extremely powerful there. And I think it's probably better to remove barriers from domain to language rather than introducing new ones like, do this in a for loop. So that's what I had to say. I recommend that we, again, as a community, we embrace this. We try to enhance this, get all of our friends and data scientists to actually embrace these ideas and work with them. And I think we'll just have better teams, we'll have better models, and be happy. Thank you very much. Appreciate it.
Sorry to scare this.
No worries. No worries.
Any questions for Aris about functional programming and how to save your ass?
You briefly, under your breath, I think you kicked Spark a little bit, which I think is appreciable. And I know you've worked with Spark a bit. Do you have any suggestions on how to work with Spark in a more functional way?
That could be a whole conversation. I was actually speaking to the architecture of how Spark is written, in the sense like I've tried to look at it from a more type class perspective, but it's like subclass, 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 subclass. That's more what I was discussing. To that extent, I mean, there's actually a lot of more, it's a long question, but you can add things like, for example, adding more descriptive types to your code, doing a little bit more work with wrappers and so forth. It's a great question, but I feel like it would be, to give it honest justice would take significant time. Anybody else? Hopefully I just made my piece or made my case here pretty well. All right, thank you very much, folks.